Okay, back to transformations. So I will talk about the Jacobian formula. So you are considering a transformation y is equal to g of x, and g of x, g is a Borel measurable function, right. So we said, so last class we showed from first principles how we can obtain the CDF of y given the probability law of x, right, and we worked out some examples, right. Today I am going to derive a formula for the density of y given the density of x under some fairly special circumstances. The special circumstances are that x is a continuous random variable, so it has a density, and g is a invertible differentiable function. Okay. Suppose x has a density f x and g is a monotone differentiable function. So g can be, so g is differentiable and g is monotone increasing or monotone decreasing, okay, and x has a density. So this is a very special case, okay, this is by no means applicable for any other circumstances. So in this case you can get an explicit formula. So here you can, so probability of y less than or equal to y, this is your CDF of y, can be written as the integral minus infinity, well it is not really minus, so it is over all x such that g of x less than or equal to y, is not it? Agreed? I am integrating over all x. After all, the probability of any set is given by the integral over that set of the density, Radon-Nikodym theorem, right. So I am integrating over the set where g x is less than or equal to y, right. So now what I am going to do, I am going to, so let me just write f x of x dx, and I am going to make a transformation. I am going to write x is equal to g inverse y, right, in this integral, put, then you will get this will be integral minus infinity to g inverse y. Well, okay, so I will, so okay, first let me write this f x of x dx. So first of all, so forget this substitution now. So let me say this one step later. So you have that. So why do you have that? Why is this true? Exactly. So I have assumed that, so first I have assumed that if g is monotone increasing, then you will have this, correct, because g s less than or equal to y will be the same as integrating from x from minus infinity to g inverse y, g also has an inverse, right. Now you make the substitution I said, right, now you put, so now you will get this is integral minus infinity to y f x of g inverse y dt over g prime of G inverse of y. So, what am I doing here? I am just putting x is equal to well t, isn't it? All this will be t, I think. This is all t, right. I am just putting x is equal to, in this I am putting x is equal to G inverse t, right. G of x is equal to t, right. So, I have that is fine, and then my dx will become. So, what I basically have is, so I have g of x is equal to t. So, g prime x dx will be dt, right. So, dx will be dt over g prime x, which is g prime of g inverse t, right. So, yeah, so this implies that, so basically this implies g, so g prime x dx is equal to dt, and therefore, dt over g prime x is what I have here, which is dx, right. So, this is your standard change of variable, right, standard change of variable, which means that my, so my f y of y must be equal to this guy over here, right. F y of y must be f x of g inverse y over g prime of g inverse y. Okay. So, I am just pulling that guy out, all right. Now, this holds for g monotone increasing. If you have g monotone decreasing, you will get a minus sign over here, okay. You can just work it out. If g is monotone decreasing, you will get a minus sign here. So, generally you can do that, you can just put an absolute value, and this will hold for g monotone decreasing or monotone increasing invertible function, okay. Okay, so this is your, so I have expressed my density of y as a in terms of the density of x, correct, and in terms of the inverse of g and this term here, which is again a function of the g's derivative and the inverse of g, right. Now, this term here is called the Jacobian of the transformation, right. This is called the Jacobian. So, it is called the Jacobian of the transformation g of x is equal to t, okay. That is why this formula is called the Jacobian formula, all right. Now, see, this Jacobian is not something, this is Jacobian is a concept you are already familiar with, you may not know it, that this is called Jacobian. So, you have done integrals since your 12th class or something, right. So, when you put x is equal to sin theta in some integral, you write dx is equal to cos theta d theta, right. That cos theta is the Jacobian of the transformation, just like here, right. I have put, so gx is equal to t, g prime x dx is equal to dt. So, this guy is the Jacobian of the transformation. You put x is equal to t square, dx is equal to 2t dt, right. So, the 2t is the Jacobian. So, the Jacobian essentially tells you, if you make a transformation from one space to another, it tells you how a small differential element in the x space scales in the other space, right. So, it has to be scaled by the Jacobian in order to give you the small differential element in the other space, right. So, this is just a one, this is just for one variable Jacobian, okay. There are also multivariable Jacobians. If you go in the space from Rn to Rm or some Rn to another transformation, you can write down the Jacobian for that as well, okay. So, is this clear? So, this Jacobian is something you already know about, you may not call it the Jacobian, but you have been using it all along, and there is really nothing new about this formula. I have just used some variable change in the integration. So, again, so I want to caution you that this formula is only useful under a very restrictive set of assumptions, that x has a density and g must be differentiable monotone increasing or monotone decreasing, okay. So, for example, the example we had yesterday, if you had y equal to e power x, x is normal 0 1, right. E power x is a monotone increasing differentiable function, right. So, you can use this formula, correct. So, what will you have? So, you will have f y of y is equal to f x is what? So, e power, so 1 by 2 pi square root of 2 pi e power minus x square over 2, but in place of x I have to write g inverse y. What is g inverse y? Log y, log y squared over 2, but I also have the Jacobian sitting in the bottom. So, I have to do derivative g prime of g inverse of y, right. So, what does that give me? So, g inverse y is what? G inverse y is, so y is equal to e power x, right. G inverse y is log y, isn't it? Yes or no? G prime y is equal to g prime of t is equal to e power t, right. G x is e power x. So, g prime t is e power t. So, g prime of g inverse y is simply y, right. So, this implies g prime of g inverse y is equal to e power log y, which is y, right. So, that guy you will get here, right. Actually I should put absolute value of y, right, but y is always positive. So, I do not have to put absolute value of y. So, this is valid for y strictly bigger than 0. I think yesterday I wrote y greater than or equal to 0, please correct it, right. This is only for y strictly bigger than 0. So, this is the same formula you got yesterday, right, fine. So, my impression is that this formula, I mean while it works out all right in this specific case, I actually feel a lot more comfortable using the first principles derivation, because there is a much smaller scope of making a mistake, or you may go something off in computing these things, right. So, I would, so while I derive this formula for completeness, I never use it, okay. I will tell you my personal opinion on it. I will just use the first principles whenever I have to compute CDFs. So, for example, even in the simple case, let us take the other example where my let us say my x is n01 and y is x squared. You cannot use this formula, right, because x square is not it is not monotonically increasing or monotonically decreasing, it has no inverse as a matter of fact, right. X square is not invertible on R, correct. So, in this case the formula cannot work. Very simple example, you cannot use the formula, right, useless, right, can't use formula, because G is not monotonic, or you have to massage it a little bit, you have to look at the positive side and negative side and do something about it, right. It is a bit of a headache. If you had, on the other hand, if you had, let us say x as exponential with parameter lambda and y is equal to x squared, okay. In this case what happens? You can use the formula, because x, see this is this works only over the positive, this density is only over the positive x axis, and therefore, over R plus this is monotonically increasing, right. So, you can use the formula, okay. Here you can just do this exercise, but still I claim that you are better off using just the first principles derivation. Okay. So, I will just do are there any questions on this? So, I will do the n dimensional version of this. Okay. So, you have more generalized version. Okay. So, you have x 1 x 2 dot 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 x n are random variables and define y 1 through y n as let us say g 1 of x 1, g 2 of x 2 and so on, g n of x n. So, this is the so this is a in this case. So, what you want is to compute the. So, given the joint distribution of the x n's, you want the joint distribution of the y n's. Okay. And here similarly, I mean a derivation, you can do a similar derivation, but you have a multidimensional transformation, right. So, your Jacobian will basically you are going from a space x 1 through x n through y 1 to y 1. So, you will have a Jacobian in these n dimensions, and the Jacobian in n dimensions will be a determinant of partial derivatives. You might have seen this in other fields as well, right. So, I will not really fuss so much about the derivation, it is it is a long, but not very instructive derivation. You are just looking for the how the differential element dy 1 dy 2 dy n transforms to dx 1 dx 2 dx n, right. So, what you have is if you have a unique pre. So, in a situation where for each y 1 y through y n there is a unique pre image in the x space, you have a similar Jacobian formula, and your joint density. So, x 1 x 2 x n random variables with joint density f x 1 x 2 x n of so this is just x 1 x 2 dot 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 x n, right. That is your joint density. Then you can write f y 1 y 2 y n of little y 1 y 2 y n as f x 1 x 2 x n of g 1 inverse of y 1 dot 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 g n inverse of y n times times Jacobian y, okay, or maybe where. So, let me write this properly. So, j of y should be like the determinant del x 1 del y 1 del x 2 del y 1 del x n del y 1 dot dot dot. So, here you will have terms like del x 2 del y 1, okay, del x 2 del y 2 del x 2 del x y y 2 del x n del y 2 and so on, and finally you will have del x 1 del y n dot 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 del x n del y n, determinant of all that. So, does this agree with what I wrote here? So, this guy is in the denominator. So, the Jacobian of y with respect to x and x with respect to y are just inverses of each other. Okay. So, I am just wondering if this and this are consistent, right. So, if you have just one function here, you have x is equal to g inverse y right dy. So, g x, so yeah, you will have g x is equal to y if you have just one function, and you will have g prime x dx is equal to dy, and have g prime x which is dy dx. I think this is correct. So, I think these two are fine, right. So, because I will have dy, so I will have 1 over g inverse x which is the same as dy dx. So, you will have, so what this guy is just 1 over dy dx which is same as dx dy, right. So, I think it is all this is consistent. So, except the Jacobian here, so the j y, so this Jacobian and the Jacobian here are inverses of each other, right. They are, this is the Jacobian of y with respect to x and x with respect to y are inverses of each other. Okay. So, I think this formula is correct. No, I was just wondering if this has to be a minus 1 here, it is not. So, this is correct. Okay. So, that is your formula. So, this is the Jacobian of the transformation from y to x, rather from x to y. This is plays the same role as this guy, right. It is, you can think of this as the 2t dt, and when you put x is equal to t squared, 2t is your Jacobian, right. This is your multidimensional Jacobian. Okay. Del x 2 del y 1, did I make a mistake? Yes, this will be del x 1, wait a second. So, this should be del x, yeah. So, this should be del x 1 del y 1, del x 2 del y 1, yeah, that is fine. This should be del x 1 del y 1, correct. Yeah, x's go that way, y's go that way, right. Del y, this is del y 2, so this should be del y 2, that is correct. Yeah, sorry. It does not matter if you go the other way, you can, the determinant after all is symmetric to flipping the main across the main diagonal, right. So, if you want you can write del x 1 del y 1 del x 1 del y 2 and so on, that is also okay. Okay, good.